Imagine, just for a second, that you work alongside this highly skilled, like intensely detail-oriented coworker.
Right, someone sitting right next to you all day.
Yeah, exactly, but digitally. They're reviewing your daily commits, looking at your logic, and generally acting as this brilliant second pair of eyes on your software architecture.
A developer's dream, really.
You'd think so, right?
Yeah.
And you've spent the last 2 months dialing in a perfect working relationship with them. You know exactly how to ask them for feedback.
You know how to interpret their critiques.
Right. But there is this massive systemic catch to the relationship. Every 2 months, this coworker just vanishes for the weekend.
Poof. Gone.
Gone. And then they undergo this fundamental structural upgrade to their entire neural architecture, and they boot back up on Monday morning.
Which sounds great on paper, but
But practically, they are a stranger. They're smarter, sure, but your entire communication protocol, the workflow you spent 8 weeks meticulously calibrating, it's suddenly at risk of completely breaking down.
it is a phenomenal logistical challenge. I mean, you are forced into this constant state of, well, operational whiplash.
Operational whiplash, I like that.
Because you have to continually recalibrate your baseline expectations of what they can do. And more importantly, you have to completely re-engineer the way you speak to them to account for that newly altered cognitive framework.
So welcome to the deep dive, because today we are dropping you right into the center of that exact high-stakes scenario.
It's fascinating stuff.
It really is, because that shape-shifting coworker isn't some hypothetical HR problem. It's the daily lived reality for software engineering teams trying to build products on top of, cutting-edge AI.
Yeah, and our entire exploration today stems from a highly revealing internal breakdown.
Right, essentially a post-mortem interview.
Exactly, conducted by the engineering team at CodeRabbit. Specifically, we're looking through the eyes of their VP of AI as they navigate the integration of Anthropic's newly released model, Claude Opus 4.7.
And what I love about this source is that it completely strips away the marketing veneer.
Oh, entirely. We aren't looking at theoretical benchmark charts here.
No press release promises at all. We are sitting in the trenches with the engineers, the ones tasked with taking raw, untamed computational power and somehow molding it into a reliable, everyday tool.
And doing it for thousands of human developers, mind you, without bringing their entire software ecosystem to a grinding halt.
Right, because getting a wildly powerful new AI model is kind of like, well, it's like buying a ridiculously powerful new sports car. You can't just drop it into your daily commute without adjusting how you drive.
That's a great way to put it. The foundational reality is that increased intelligence introduces entirely new vectors for failure.
Wait, really? Being smarter makes it fail more?
Well, upgrading an LLM isn't like updating your smartphone's OS where things just run a little faster. Every new reasoning capability fundamentally alters the equilibrium of the platform.
So to understand the sheer scale of the disruption we're talking about, we have to look at the very first thing the CodeRabbit engineers noticed when they plugged Opus 4.7 inches.
Out of the box.
Right out of the box, because it wasn't a spike in processing speed or memory allocation. The most immediate shock to the system was a radical shift in the model's personality.
Yeah, they experienced a massive, fundamental alteration in tonality.
Which is wild.
It is. And in the context of automated code review, where a machine is essentially critiquing human labor, tonality is the absolute bedrock of user trust.
Right. Nobody wants to be yelled at by a robot.
Exactly. The transition from Opus 4.6, which they had integrated just 2 months prior, to the new 4.7 architecture, it brought this severe adjustment in how the model positioned its own authority.
Let's look at the baseline behavior of the predecessor first, Opus 4.6. The engineering team noted that just a few weeks ago, this model functioned heavily on, defensive hedging.
It communicated like an incredibly anxious junior developer.
Yes, someone terrified of stepping on a senior engineer's toes. When 4.6 found a flaw in the code base, it would generate these highly couched, inclusive statements.
Very timid.
Very. It would write things like, this might potentially be an issue, you should perhaps consider looking into it, or I think there is a possibility we should think about fixing that.
Right, it was an architecture optimized for safety over assertion. It wrapped every single diagnostic observation in layers of synthetic politeness and plausible deniability.
I mean, if a human reviewer left that kind of hesitant, overly cautious comment on my pull request, it would drive me absolutely crazy.
Oh, it's maddening.
The cognitive load of trying to figure out if they actually found a bug or if they are just musing about coding philosophy, it's exhausting.
And that's exactly why tonality matters.
But the moment the team routed their systems to Opus 4.7, that timid intern just vanished.
Completely gone.
The VP of AI explicitly documented that 4.7 operates with the tonality of a highly assertive senior principal engineer. The hedging was just stripped away.
It suddenly began dropping definitive statements like, we should look at this immediately.
Or just pointing to the code and stating, this is broken, here is the flaw.
We have to look at the mechanics of why that tonal shift is so disruptive, though, because it goes beyond simple user preference.
Okay, lay it out for us.
A model that perpetually hedges its bets inevitably trains the human user to ignore it.
Ah, like the boy who cried wolf, but politely.
Exactly. If the AI constantly signals that it isn't entirely sure of its own findings, the human developer, who is already pressed for time, will simply stop investigating the flags.
They just calculate that the risk of the AI hallucinating is higher than the risk of the bug actually making it to production.
Precisely. They tune it out.
But hold on, if the AI is making affirmative, highly confident assertions now, doesn't that inherently increase the risk of a catastrophic failure?
That's the danger, yes.
Because if the anxious intern is wrong, you roll your eyes and dismiss it. But if a highly confident senior system tells you to rip out a chunk of code and that system is hallucinating...
You might blindly follow that advice and actively break your own production environment.
Right. Confidence without underlying accuracy is just automated arrogance.
That is the exact tightrope the engineering team is walking.
Yeah.
Arrogance in software architecture introduces critical vulnerabilities, and the VP of AI highlighted this dynamic to emphasize a concept known as prompt drift.
Prompt drift. Okay, break that down for us.
You have to remember that the CodeRabbit platform is essentially a massive wrapper of system prompts communicating with the Anthropic API.
Right, they are just sending instructions to the engine.
Right. So when you have a prompt optimized for Opus 4.6 that says, be definitive and clearly point out errors, it pushes that timid model toward a balanced, acceptable tone.
Ah, I see, because you are applying an aggressive prompt to a passive baseline model, so they meet in the middle.
Exactly. But when the underlying model architecture changes to Opus 4.7 model, whose baseline is already highly assertive, that exact same static prompt suddenly acts as a massive multiplier.
Oh, wow. So you are now feeding an aggressive instruction into an aggressive architecture.
Yes. And the resulting output isn't just confident. It becomes highly abrasive, overly bossy, and actively degrades the user experience.
It just annoys the developers.
Completely. The instruction hasn't changed, but the mathematical interpretation of that instruction has shifted entirely.
So you essentially have to sit the new model down for couples counseling with your legacy prompts.
That's a good analogy.
You have to tell 4.7, we appreciate your newfound confidence, but we need you to dial the aggression back 20% so our developers don't uninstall the application.
It really highlights that integrating these systems is a constant exercise in behavioral management.
But of course, dealing with an assertive AI is only worthwhile if the model actually has the brains to back it up. We need to look at the raw performance data to see if 4.7 earned its swagger.
And the internal benchmarks prove that the tonal shift was backed by a very real leap in capability. They recorded a roughly 15% aggregate improvement in raw reasoning and processing power.
Compared to the 4.6 architecture.
Right. And the way they measure that improvement provides a really fascinating look into how AI utility is quantified in the real world.
Yeah, they use a dual benchmark approach, which I find incredibly telling. The first set of evaluations is what they categorize as the brain teaser set.
These are highly complex synthetic data environments.
Right, designed to push the absolute limits of the model's multi-step logical reasoning.
You can think of the brain teaser set as an evaluation of the model's computational ceiling. They are testing its ability to diagnose incredibly deep structural flaws, like complex concurrency bugs.
Remind me, a concurrency bug is when multiple threads try to access the database at the exact same time, right?
Exactly. Independent threads trying to read and write at the exact same millisecond, creating a race condition.
That sounds like a nightmare to find.
It is. To spot a flaw like that simply by reading static text, the LM has to hold the entire architecture in its context window. It'd have to map out the chronological execution of different functions and recognize that two disparate pieces of logic will eventually collide.
It basically has to hold incredibly complex, multidimensional truth in its head, or, well, its synthetic memory. But as the VP of AI noted, those massive catastrophic concurrency bugs are actually quite rare in the daily life of a software engineer.
Very rare. You might see a true architectural brain teaser a few times a year.
Right, which is why CodeRabbit relies much more heavily on their second benchmark, the real-world set.
The real-world set shifts the evaluation from sheer logical depth to horizontal context engineering. It tests the model against highly pernicious everyday bugs.
So not structurally complex flaws.
No, not at all. A junior developer can fix them in 2 minutes once they are identified. The difficulty lies entirely in spotting them amidst a sea of otherwise functioning code.
They're like the typos of the logical world, the kinds of mistakes a brilliant human engineer makes at, 4:00 p.m. on a Friday because they are slightly undercaffeinated and staring at their fourth monitor.
Spot on. It requires the AI to synthesize large amounts of surrounding context, filter out the noise of the standard boilerplate code, and isolate a tiny contextual error.
And the data showed that Opus 4.7 dominated both benchmarks. It navigated the deep race conditions, and it isolated a vastly higher percentage of the everyday bugs.
In data science terms, its recall rate, its mathematical ability to retrieve and flag existing errors, skyrocketed.
So raw intelligence goes up, recall hits an all-time high, the model is catching everything. On paper, this is a massive victory, right?
On paper, yes.
But the real-world deployment of that increased recall immediately triggered a systemic crisis for the platform. The engineers realized that a pure, unconstrained improvement in intelligence completely broke their user interface.
It's what the team described as flooding the space.
Flooding the space. What does that actually look like for the user?
It is the nightmare scenario of high recall information retrieval. By improving the model's ability to spot every conceivable flaw, they inadvertently destroyed the precision of the output.
Because the model stopped prioritizing.
Exactly. It began generating an absolute avalanche of major, minor, and microscopic comments on every single pull request, utterly overwhelming the software ecosystem.
Let's look at the psychology of the human developer receiving this. Imagine you hire a hyper-vigilant home inspector before buying a house. You want that inspector to have a high recall rate for structural integrity, right?
Absolutely. You need to know if the foundation is sinking or if the roof trusses are rotting.
Or if the main electrical panel is a fire hazard. Those are your system crashing concurrency bugs. But imagine that same inspector hands you a 500-page dossier on the property.
And 480 pages of that report are dedicated to documenting every single microscopic scuff mark on the baseboards.
Yes. Every slightly misaligned cabinet hinge, every light switch plate that is a fraction of a millimeter off-center, every single thing they flagged is technically a flaw. Their recall is flawless.
But you, as the homebuyer, are completely paralyzed by the sheer volume of data. You cannot physically locate the warning about the rotting roof because you are drowning in a sea of data about crooked light switches.
Exactly. Alert fatigue sets in immediately.
When Opus 4.7 began flooding the space with minor, technically correct, but practically useless observations, it violated the core utility of the product.
If developers have to sift through 50 minor stylistic critiques just to find one critical security vulnerability,
They'll just close the application and stop using AI code review entirely.
So they had a massive engineering dilemma. They needed to force the new architecture to stop pointing out the crooked light switches. But any blunt force attempt to constrain the model risked accidentally blinding it to the rotting roof trusses.
They needed to surgically increase precision without sacrificing the newly gained recall.
And the methodology they used to solve this is, and I mean this without exaggeration, one of the most fascinating aspects of modern AI engineering detailed in this source.
Yearly is an incredibly elegant approach to managing synthetic logic. To cure the comment flooding, the VP of AI explained how they implemented a self-improving prompting engine.
Because having human engineers manually review chat logs and guess why an AI generated a specific useless comment is just a massive waste of human capital, right?
It's too slow and entirely unscalable when you're dealing with a dynamic code base and a model as complex as 4.7.
So instead of humans trying to debug the AI, they forced the AI to psychoanalyze itself. They built an auto-tuning metal loop that essentially acts as behavioral therapy for the model.
AI therapy, essentially.
I love that. Let's look at the mechanics of this loop, because the architecture is brilliant. The platform meticulously records the entire diagnostic trace log of the AI's interaction with the code.
And this isn't just the final comment the AI leaves. It includes the system prompts it was fed, the specific chunks of code it analyzed, and the latent internal thought processes it navigated to arrive at its conclusion.
Right, so when the engineering team identifies a failure in precision-like, the model leaving a highly verbose, completely unnecessary comment on a standard variable declaration, They don't rewrite the system prompt themselves.
No, they isolate that specific trace log and feed the entire package back into Opus 4.7.
They hold up a digital mirror to the model. They supply it with its own recorded output and present a meta prompt, basically saying, you generated this comment. It's low value, it degrades user experience. Analyze the state of the system at the exact moment of generation.
What specific instructions in my prompt, or what contextual parameters, led you to the conclusion that this comment was necessary?
This is where that advanced multi-step reasoning of the 4.7 architecture is utilized, not for code review, but for structural self-reflection.
Exactly. The model processes its own historical state. It parses the overarching system prompts, the specific user instructions, the local code context, and traces its own logical pathways backwards.
And it actually possesses the capability to successfully isolate the exact semantic trigger that caused the failure.
It will return a diagnosis saying, in paragraph 2 of the main system prompt, you provided the instruction. Ensure all variables adhere to strict documentation standards.
And it recognizes that constraint was overly broad.
Because it lacked a specificity threshold. The model computationally latched onto that instruction and executed it universally, resulting in minor comments on every obvious variable in the file.
The diagnostic capability alone is impressive, but the meta loop goes a step further, right?
It does. The engineers then require the model to explicitly rewrite the system prompt to eliminate the behavioral flaw it just diagnosed.
They're essentially asking the machine to rewrite the constraints of its own operating parameters.
Yes.
Wait, let's examine the underlying logic of that process because it presents a massive paradox.
Okay, let's hear it.
If the 4.7 architecture is intelligent enough to retroactively look at a trace log, perfectly diagnose its own behavioral flaw, and rewrite the prompt to guarantee it never makes that mistake again, why did it generate the useless comment on the very first pass?
That is the big question.
If it fundamentally understands what a bad comment is during the therapy session, why didn't it filter that comment out during the actual code review?
That paradox is the defining characteristic of working with large language models. You have to separate the model's capabilities from its operating constraints.
Okay, separate capabilities from constraints.
Models do not possess intrinsic, human-aligned common sense. They operate strictly within the mathematical constraints provided in their active context window.
Right.
During the initial code review, the model's absolute constraint was the vague instruction to ensure documentation. It executed that constraint perfectly without any awareness that it was violating a secondary, unstated human desire for a clean user interface.
It is the literal execution of the genie in the lamp.
The genie in the lamp, perfect analogy.
You wish for $1 million and the genie materializes 1,000,000 male deer inside your living room, crushing your house.
It executed the prompt flawlessly based on the semantic constraint provided.
But it completely violated the unstated human intent of the wish.
Exactly. The AI does not conceptualize the initial flood of comments as a mistake. It views it as total compliance.
It's just doing its job.
Right. It is only when the human engineer intervenes, flags the output as a failure, and initiates the meta loop that the model is given a new explicit constraint. Evaluate this output against the concept of user fatigue.
So the therapy loop is entirely a mechanism for transferring implicit human intent into explicit mathematical constraints.
Yes, and VP of AI detailed how the human engineers review the model's suggested prompt revisions, generalize them so they apply to the broader system, and deploy them back into the platform.
It transforms prompt engineering from this mystical dark art where developers just blindly tweak adjectives and hope for the best into a rigorous, iterative software engineering process.
They utilize an evaluation harness to run this loop rapidly and at scale. And through this process, they successfully reached an equilibrium where they maintained the 15% increase in complex bug recall, but surgically filtered out the low-value noise.
They tuned the precision to match the power.
Precisely.
But dialing in the precision of the prompt only solves the behavioral side of the equation, right? Once you've optimized what the AI is supposed to be looking for, you immediately run into the hard physical limitations of modern computing.
You have to strictly manage how much computational effort the AI is allowed to expend looking for it.
Because in software, time is money. This introduces a critical architectural shift in how Anthropic manages inference, shifting from static budgets to dynamic adaptation.
In the realm of automated software engineering, theoretical brilliance is utterly irrelevant if it takes too long to execute or costs too much to run.
We're looking at the strict economics of thought. The internal breakdown highlighted a massive operational change between managing the older 4.5 architecture and the new 4.7 release.
Historically, the CodeRabbit engineers were forced to manually manage the model's computational expenditure using what were known as thinking budgets.
Thinking budgets, and those were highly manual, right?
Highly manual, highly stressful configuration requirement. Whenever a human developer submitted a pull request for review, the underlying system had to run a pre-computation heuristic to guess exactly how many tokens the AI would require to process the code.
A token being the fundamental subword unit of computational currency the model consumes.
Right. The engineering team had to build complex, predictive logic just to decide how much fuel to put in the AI's tank.
They had to look at a chunk of code and guess, this looks like a highly complex architectural change. Allocate 15,000 tokens so it has enough runway.
Or this is a simple text change, only give it 500 tokens.
And if their heuristic guessed wrong on a complex problem,
The AI would literally run out of tokens mid-thought and return a broken, half-finished review.
yikes. That forces the human engineers to micromanage the internal processing state of a supercomputer.
Which is terribly inefficient. To eliminate that friction, Anthropic introduced a paradigm shift known as adaptive thinking.
It started as an experiment in 4.6, right?
Yes, but the VP of AI confirmed it is now the mandatory operating standard for 4.7. The manual token budget has been entirely deprecated.
So instead of a strict budget, developers now configure an effort parameter. It's a sliding scale of computational allowance, ranging from low, medium high, extra high, up to max.
This parameter does not dictate the exact number of tokens the model must use. It establishes the maximum ceiling of effort the model is authorized to expend if the problem requires it.
The theoretical design of adaptive thinking is highly elegant. If you configure the effort parameter to max, and you hand the model an incredibly simplistic problem, like a missing semicolon on line 4,
The model should dynamically recognize the simplicity of the task. It should expend a tiny fraction of its compute, output the obvious solution, and immediately terminate the sequence.
completely ignoring the massive computational ceiling available to it.
Exactly. It adapts its effort to the reality of the code.
But again, the theoretical design immediately collided with the messy reality of LLM architecture. When the team actually deployed this with the effort set to max, they uncovered a severe systemic flaw.
The model began suffering from massive, unconstrained overthinking.
Overthinking.
It's a deeply documented phenomenon with highly capable models when they are provided with an excess of computational leash. The architecture is designed to explore probability spaces.
So even on a simple problem, if it knows it has the max budget, it just keeps digging.
Yes, its internal routing might dictate that it explore incredibly low probability edge cases. It will wander down massive theoretical rabbit holes, analyzing impossibly rare systemic interactions, before eventually concluding that the obvious answer was correct all along.
It is the exact behavioral dynamic of giving a 16-year-old a $1,000 budget and dropping them off at the grocery store with instructions to buy a gallon of milk and a dozen eggs.
That's a great way to visualize it.
If you give them exactly $10, they walk straight to the dairy aisle, execute the transaction, and are back in the car in 5 minutes. Their physical constraints force an efficient operational path.
They execute the minimum required logic to fulfill the constraint.
But if they have that entire $1,000 budget burning a hole in their pocket, even if they intellectually understand they only need milk and eggs, the sheer availability of resources alters their behavior.
They are going to wander the aisles for 2 hours.
Yes, they will browse the electronics section, deeply analyze the nutritional content of the snack aisle, evaluate the geopolitical supply chain of 6 different brands of imported cheese.
And they will eventually bring the milk and eggs to the register, but the time expenditure is catastrophic.
Exactly.
That dynamic perfectly illustrates the critical metric of test time compute. In AI engineering, test time compute represents the literal, measurable budget of time you are willing to force a human being to wait while the model runs its inference processes.
Because while the model is wandering the computational grocery store analyzing edge cases, the human developer who submitted the code is sitting at their desk staring at a loading bar.
The latency of the system goes through the roof. And in the workflow of software engineering, high latency is a death sentence for user adoption.
Developers operate in a delicate flow state, When they submit a pull request, they need the feedback loop to be tight.
If they have to wait 20 minutes for an overthinking AI to finish its maximum effort analysis, their context window shatters.
They will pivot to checking emails or picking up a different Jira ticket. By the time the AI finally returns its incredibly detailed analysis of the milk and eggs, the developer has entirely moved on.
The value of immediate contextual feedback is destroyed.
So the team had to rein in the overthinking. They couldn't let it run at maximum capacity. How did they actually force the model to behave efficiently without breaking its ability to solve the hard brain teasers?
They systematically tuned the effort parameter downward. By running vast amounts of historical pull requests through the model at varying effort levels, they mapped out the optimal computational threshold.
Finding the sweet spot.
Exactly. They found the exact setting that provided enough ceiling to untangle complex concurrency issues, but constrained the model just enough to prevent it from wandering into theoretical rabbit holes on simple tasks.
And the recorded outcome of this tuning process is wildly counterintuitive. The source noted that by aggressively lowering the effort parameter ceiling and combining that constraint with the newly optimized prompts from their MetaLoop therapy,
Opus 4.7 actually achieved lower total latency and consumed fewer overall tokens than the older, theoretically less powerful models.
which is incredible. They made a heavier, more complex architecture run significantly faster simply by artificially limiting how hard it was allowed to look at the problem.
It is a profound architectural lesson. The raw, default state of a cutting-edge foundational model is almost never optimized for enterprise production environments.
The art of integration isn't unleashing the model's power. It is meticulously constraining that power to match the strict temporal and financial realities of the human workflow.
That's the reality of AI engineering.
Let's look at the totality of what this engineering team has accomplished. They managed the abrasive personality shift. They utilized iterative meta loops to dial in the precision of the prompts and stop the overwhelming flood of minor comments.
And they rigorously tuned the test time compute parameters to ensure efficiency.
Right. Once all of those constraints are perfectly balanced, what does the output actually look like? What specific engineering feats can this highly optimized Opus 4.7 architecture achieve that previous generations fundamentally could not?
When the model is tuned correctly, its increased capacity for multi-step reasoning allows it to break entirely out of the structural boundaries we have historically used to contain automated code review.
It begins executing what the team classifies as outside the diff analysis.
Right. And to grasp why outside the diff analysis is such a massive paradigm shift, we have to look at the rigid constraints of modern version control platforms, primarily GitHub.
Okay, let's talk about the diff. When a developer writes a new feature and submits it to the repository, GitHub generates a visual representation of the exact mathematical difference between the old code base and the new submission.
It highlights only the specific lines of text that were added, modified, or deleted.
And historically, the entire ecosystem of code review has been strictly confined to that tiny, isolated box.
If a developer modifies line 40 of a script, the AI was historically constrained to analyzing the logic of line 40.
But modern software architecture doesn't exist in isolated vacuums.
Not at all. A modification on line 40 might execute its local logic flawlessly, but because of complex dependency chains, that same change might silently break an API endpoint on line 800.
Or fatally corrupt a database query in an entirely different file stored 3 directories away.
Previous models simply did not possess the context window or the multi-step reasoning required to trace those sprawling horizontal dependency chains.
But Opus 4.7, running inside CodeRabbit's context engineering harness, is no longer looking at just the isolated diff.
It is actively reading the surrounding files, evaluating the imported libraries, and parsing the historical execution logs of the associated functions.
It is holding all of these disparate data points in its synthetic memory simultaneously and mapping out the cascading effects of a single line of code across the entire architecture.
The model ceases to be a mere syntax checker and evolves into a holistic architectural auditor.
And because it's injecting vast amounts of historical context into its reasoning engine, the VP of AI documented instances where the model begins flagging systemic vulnerabilities that aren't even tangentially related to the new code being submitted.
The model is actively, retroactively auditing the past.
It's like archaeology. You could be a developer submitting a tiny 2-line formatting fix on a Wednesday morning, and the 4.7 architecture will process your diff, analyze the context, and essentially tap you on the shoulder.
Your formatting fix is perfectly fine. However, my multi-step reasoning engine recognized that a different developer introduced a deeply buried logic flaw into this underlying dependency 6 months ago.
It has been silently degrading system performance ever since. You need to repair this legacy flaw. That is mind-blowing.
It acts as an automated archaeologist, surfacing latent technical debt that human reviewers glossed over for half a year.
The implications for the long-term structural health of massive enterprise repositories are staggering. If the model is constantly cross-referencing new submissions against historical context, the density of hidden, festering vulnerabilities steadily approaches zero.
Drastically reducing the surface area for catastrophic production outages.
It is an incredible display of computational reasoning. But introducing that level of historical archaeology into a daily workflow forces us to confront the final and arguably most difficult challenge detailed in this internal breakdown.
Right, because if the AI is suddenly digging up ghosts from the past, flagging 6-month-old mistakes,
Expanding its critique far outside the boundaries of the developer's immediate work, how do you mathematically prove that the human developer actually wants that information?
you are transitioning from the objective realm of computer science into the highly subjective realm of human psychology and UX design.
We are talking about the absolute difficulty of measuring the concept of good.
Determining whether a code base contains a logic flaw is a deterministic process. The code will either execute or it will fail. But determining whether an AI's comment about that flaw is good is a fluid, entirely subjective evaluation of the human experience.
Because the most computationally brilliant architectural analysis in the world has zero practical value if the deliver mechanism annoys the humans so much that they refuse to read it.
Exactly. So, since they cannot write a mathematical formula to prove a comment is subjectively good, the CodeRabbit team relies on a constellation of secondary proxy metrics to evaluate the integration.
They track the digital footprint the AI leaves on the platform. The first proxy metric they rigorously evaluate is readability.
And to measure this, they strip away the code and analyze the AI's output using standard linguistic complexity models, primarily focusing on variations of flesh-reading ease algorithms.
They evaluate the sheer cognitive load required to parse the AI sentence structure. The VP of AI drew a very stark contrast here. If you deploy Model A, and it successfully identifies 100 structural bugs.
And then you deploy Model B, and it identifies the exact same 100 bugs, but Model B requires twice the amount of text, utilizes denser vocabulary, and includes rambling philosophical justifications for every finding.
Model B is actively degrading the platform.
Verbosity and automated tooling is a direct tax on a developer's time. Engineers utilize these platforms to increase their velocity, not to read synthetic dissertations on coding theory.
If the linguistic evaluation indicates the model is generating high-friction, densely packed paragraphs, the developers will simply skim the text.
Inevitably missing the critical diagnostic data buried inside the noise. So optimizing readability is the baseline requirement.
But the second metric they track is where the true value of modern AI integration is unlocked.
The second metric is actionability. Does the AI simply act as a critic standing on the sidelines pointing out flaws? Or does it step onto the field and actively help resolve them?
The absolute gold standard for actionability in this context is the model's ability to generate a functional patch.
A patch being the precise, syntactically correct block of code required to overwrite the flaw and repair the system.
The source explicitly notes that human engineers universally respond positively when the AI transitions from diagnostic mode into generative mode.
It completely shifts the dynamic of the interaction.
The model isn't just saying, your database query on line 40 is inefficient. It is saying, your database query on line 40 is inefficient. Here is the fully optimized, syntactically verified replacement query.
Click this single button to merge my code into your branch and resolve the issue immediately.
The friction of code review drops to near zero.
And when you successfully balance high readability with high actionability, it inevitably drives the third and ultimate metric, business outcomes.
This is where subjective human feelings are translated into hard operational data. The team monitors the granular telemetry of the platform. Do the developers actually click the button to accept the AI's generated patch?
Do they respond to the AI with positive reinforcement? And at the macro level, does this interaction drive enterprise retention and new user signups?
Because if the model is hyper-accurate but linguistically exhausting and refuses to write patches, the patch acceptance rate plummets, churn increases, and the business metrics collapse.
The integration of Opus 4.7 is a massive success, not simply because the model is smarter, but because the engineering team spent weeks painstakingly tuning its behavior to ensure it drove those specific business outcomes.
The VP of AI was highly transparent about the sheer volume of labor required to achieve that alignment. He estimated that migrating a platform from Opus 4.6 to 4.7 requires a minimum of several weeks of dedicated, full-time engineering effort from senior AI specialists.
Just to map the behavioral drift, execute their prompt therapy loops, and stabilize the secondary metrics before even considering a public rollout.
That specific detail presents a massive reality check for the broader software industry. I mean, if a highly funded tech company with dedicated AI executives requires weeks of intensive manual recalibration just to survive a minor version bump.
From 4.6 to 4.7.
Right. How does a smaller engineering team or solo founder survive this ecosystem? The AI landscape is advancing at breakneck speed. Is this exhausting cycle of constant manual prompt tuning just the unavoidable cost of doing business in the AI era?
It is a formidable operational hurdle, but the expert from CodeRabbit provided a very clear, highly actionable methodology for smaller teams looking to survive the velocity of these updates.
What's the secret?
His core synthesis was that while every new model release fundamentally resets the rules of engagement, smaller teams do not have to rebuild their evaluation metrics from scratch every single time.
Provided they build a systematic baseline architecture right now.
Exactly. He advocated for the immediate creation of a golden dataset. You don't try to boil the ocean and anticipate how Opus 5.0 will behave next year. You focus entirely on documenting exactly how your system interacts with the current model today.
You institutionalize the observation of edge cases. Whenever your human developers notice the AI executing a truly brilliant multi-step deduction, you capture that entire interaction, the prompt, the code context, the trace log, and the output.
And conversely, whenever the AI hallucinates, floods the space with noise, or generates a broken patch, you capture that failure state with the exact same rigor.
So if a small team commits to capturing just one specific, highly contextual interaction per day within a single fiscal quarter, they have constructed a proprietary dataset containing roughly 100 distinct behavioral benchmarks.
Mapping exactly how their specific code base reacts to synthetic logic. And that proprietary dataset becomes their operational anchor.
Because when Anthropic inevitably releases the next major architectural shift, the small team does not need to spend weeks manually guessing how the new model will behave.
They simply route their existing dataset of 100 benchmark interactions through the new API and utilize automated drift analysis to instantly map the delta.
They can immediately see, mathematically, which specific prompts improved, which logic paths degraded, and exactly where the new model is failing their readability or actionability standards.
It transforms the overwhelming mountain of an AI upgrade into a targeted systematic process.
A targeted process rather than an insurmountable mountain. It allows a 5-person startup to manage the chaotic reality of shifting neural architectures without burning their entire engineering bandwidth.
If we pull back from the specific implementation details of CodeRabbit and examine the overarching narrative of this internal breakdown, a very clear meta-trend begins to emerge.
The technical evolution from Opus 4.5 through the cautious hedging of 4.6 and arriving at the highly optimized, constrained efficiency of 4.7.
It signals a fundamental shift in how the industry is conceptualizing artificial intelligence.
The era of the verbose, overly cautious model that rambles through its thought processes to prove its intelligence is coming to an end.
The new architectural imperative is ruthlessly focused on efficiency. It is the realization that raw, unconstrained computational power is actually a liability in a production environment.
The future belongs to systems that have mastered test-time compute, models that can execute incredibly deep multi-step archaeology across historical code bases, but do so within the strict, unforgiving latency budgets dictated by human attention spans.
The AI is stepping out of the rigid confines of the visual diff, surveying the entirety of the software architecture and aggressively generating the exact patches required to secure the system.
All while communicating with the brief, definitive tonality of a principal engineer. It represents a massive recalibration of the baseline relationship between the human and the machine.
Truly a paradigm shift.
Which brings us to a final structural question for you to consider as you evaluate the trajectory of your own industry. We began this exploration by framing the AI as a highly skilled coworker, an entity that required constant management, behavioral therapy, and strict computational boundaries just to ensure it didn't overwhelm your human developers with noise.
Right.
But if architectures like Opus 4.7 are already capable of operating with extreme assertion,
If they are already executing retroactive sweeps of entire repositories to identify and isolate human errors committed months in the past.
and if they are already directly generating the syntactically perfect patches required to repair those errors with a single click, at what specific point on this developmental curve does the human reviewer cease to be the operational safety net for the AI, and the AI fundamentally becomes the operational safety net for the human?
A provocative thought.
Are we rapidly exiting the era where AI assists developers and crossing the threshold into a reality where the AI manages the structural integrity of the code base and the human developers merely assist the AI in executing its vision? Keep an eye on the latency of your next code review. The answer might arrive faster than you think.